Now let's continue with capacitors. This is gonna take us. This video is going to be about the different types of capacitors. So we are going to start with the mica. Mica capacitors are small with high working voltage. The working voltage is the voltage limit that cannot be exceeded. So capacitors can get damaged. So like we explained in the previous video, if we compact the charges inside the capacitor, yes, we can get a higher capacitance, but there is a limit to it before the capacitor plates get depleted and the capacitor get destroyed. So we cannot just add in 1,000-volt battery to a tiny capacitor and say, okay, now you're gonna hold this voltage. No, it has a limiting factor, and that is known as the working voltage. So if we exceed the working voltage, then the capacitor is going to be damaged. So the way this mica capacitor works is that it has different plates. Plates are stackable. They are stackable, and the way they are stackable is that they are connected in series, so that the voltage can be add up. Because if we remember, if sources are connected in series and they are connected in series in the right way, then the voltage can be add up. If they were connected in parallel, then the voltage will be the same. It doesn't matter how many layers we have, but in this case they are connected in series, and so the voltage is add up. The next one is going to be ceramic disc. Ceramic discs are small, non-polarized capacitors. They have relatively high capacitance due to high electrolytic coefficient. So these ceramic discs are widely used because they are non-polarized. Meaning having a capacitor that is non-polarized means we don't have to worry about where is the positive and where is the negative of the two terminals. That is important, and they are usually smaller, very compact, so they are very user friendly when you're designing, because when you're designing you want to make designs small, practical, that you can fit it everywhere. So these ceramic discs are a good candidate. Also, the area can be small due to that we have a high dielectric coefficient. So the dielectric coefficient, remember, the capacitance is defined as the electric coefficient times the area divided by the distance. So the distance can be very small and this can be very high. You get a very high capacitance. And that's exactly what this is happening here. So they are labeled in different parts of it right here. There's the lead wire is to the silver electrolyte. We have the soldering, the ceramic isolator right here, dipping phenolic coating, and we have the other connector right here. So that is the ceramic disc. We have a plastic film. Plastic film capacitors are small and non-polarized. They have relative high capacitance due to large plate area. So right here is another design. Again, this is non-polarized, so it doesn't matter, it doesn't have positive or a negative, but these ones are larger than the ceramic disc, because its capacitance gets increased due to the plate area. So here, these ones are probably the ones we used to see on those old TVs that have the big, they were not skinny TVs, but the fat TVs. They were probably used there because they are big, but because they are big, they are high capacitance. So they are practically not in use anymore. Unless you are in high power, then you will see these capacitance. But otherwise, in electronics, everyday electronics, we don't see them. Then we have electrolytic capacitors. Electrolytic capacitors are widely used because they have a high capacitance, and they are but they are polarized. So let's see what they say here. Electrolytic capacitors have very high capacitance, but they are not as precise as other types and tend to have more leakage current. Electrolytic types are polarized. Yes. So polarized, it means you have a positive and a negative, and if you don't connect it properly, it will explode. It will explode because you're connecting the negative to the positive, and you're pushing that into it through the battery until the two plates are going to deplete it and it's going to explode. So this is dangerous when you're doing a lab. You have to be very careful because it will explode. It can be a drastic explode depending on the size of the capacitor. You can burn yourself. The smoke is going to come out and it's going to become irreparable. So they are used because they have high capacitance, but we see that it's not precise. It's going to have a leak current, which means it's going to have an internal resistance that is going to create that issue. So electrolytic capacitors have a different symbol. We have the straight for the positive and the curve end for the negative. Usually they have a, like this is the more common electrolytic capacitor you will see. For the negative, you have a black strip right here going across, indicating that it is a negative polarity for that, so you cannot miss it. Okay, this type of kind of ceramic looking electrolytic capacitors has a positive or negative. This is usually, I haven't seen them being used lately. These are the most ones that we use, but yes, they come into different packaging representations. So very used because high capacitance, a small packaging, but they are not precise, and you have to take into account the polarity. Then we have, of course, variable capacitors, just like we have variable resistance. Variable capacitors typically have a small capacitance values and are usually adjusted manually. A solid state device that is used as a variable capacitor is the vector diode. It is adjusted with an electrical signal. So yes, so capacitors that we use adjust manually, you'll see that it has a knob that we can move, and then we have to have a multimeter reading capacitance so that we know what is the value of it. There is no other way you can find out, just like with resistors. Or if you want to use a solid state device, then you have to be sending a signal, a power signal, electrical signal, to the capacitor so it can be adjusted. So those are a little bit more complicated because you have to have tabulated that depending on the amount of the capacity of the signal, that's the value of the capacitance. So that's for that. Now, how do we read capacitors? You see how we learn how to read resistance depending on the color code. So capacitors are a little bit easier. The way they have labeled them, it's a little bit different. So let's go ahead and learn how they are read. Capacitors use several label methods. So on contrary to the resistors, they are not standardized. So you have to be careful when, depending on the capacitor you are using. They usually have a table, a reading table for codes, or a way of reading them. So we are going to have several examples of how is it that they use it. So capacitors use several labeling methods. Small capacitors values are frequently stamped on them, such as 0.001 or 0.01, which have implied units of microfarads. Electrolytic capacitors have larger values, so are read as microfarads. The unit is usually stamped as microfarads, but some older ones may be shown as MF or MMF. So yes, so there is not a standard way of reading capacitance. So in here, if you see a dot followed by a value, and it is a ceramic, it's not a electrolytic capacitors, then we assume that it is into the microfarads. If it is an electrolytic, it will tell you the value of the capacitor with the units, as in this case microfarads. So Don't think it is mega farads. That would be a huge capacitance. Capacitors are usually 1 or less farads. So this means microfarads, okay? And indicating the positive, you see, we have the plus with this lead, and it should be a negative going out from this lead as well. So let's stop right here.